Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU, Bhilai. In this tutorial, we discuss the topic about bee trees. In the previous tutorial, we discussed about the trees, types of trees, as well as the avial trees, and we also understand the concept of M-way tree, or we can say multi-way trees. Now, there is having some limitation, some restriction, some drawbacks in a M-way tree. No doubt M-way tree is an extended version of binary tree, but little bit having a complexity, little having a drawbacks in the M-way tree, because that particular tree, the M-way tree, is not a balanced tree. So when we feeding an item in an M-way tree, is really you're having a free to insert your item anywhere. But the problem is that the time complexity as well as the space complexity. Because you're having a freedom, you can insert a new item in anywhere, any place. There is no any restriction to insert your item in a particular format. Also, during this, the space complexity will be increases. Also, when we going to searching operation, any kind of operation like a searching, insertion and deletion, time complexity also increases when any structure in an unsystematic way, when you're feeding your data in an unsystematic way. Now, suppose we arrange a student in an unsystematic way and we fetching any item, any student in that particular structure, that is quite difficult. Definitely we get the data, but it will take a time. So, as a time complexity is also increases. So, for this one, when we want to reduce, so we having a main motto when we going to perform any operation, we are having a two motto when we performing any operation inside this. The first one is a space complexity, we have to reduce the space, and second one is we have to reduce the time also. So, there are two complexities, space complexity and time complexity. Based on these two factors, we have to design a new structure that is called a bee tree. So, that is a drawback of M-way tree, which is not a balanced tree. Now, this is a bee tree, this is a balanced tree. We can say this is a bee tree, or we can say balanced tree also. Already we studied one concept in a avial tree. Avial tree is extended version of a binary tree, but it is having a restriction in a avial tree, it can't generate more than 2 children. But in a bee tree, it's an extended version of M-way tree, it will produce more than 2 children as per the order of M. So, bee tree follow all the property of M-way tree, only a one difference. That difference is that this tree is completely a balanced tree. For this way, we reduce the space complexity and the time complexity in a bee tree. So, one by one I want to tell you how we reduce that one and how we perform all the data structure operation in a bee tree. So, first we go for the introduction part, or we can say definition part. So, bee tree is a specialized M-way tree that can be widely used for disk access. Disk means hard disk. When you feeding your data inside your data structure, by the help of data structure, you feed your data in a hard disk, you easily access your data from the disk in a minimum time. And also when you feeding your data, it will take a less memory. That is the main motto. So, how we insert, how we fetch our data inside the data disk or hard disk. So, it can be widely used for the disk access. A bee tree of order M. Order M is again already we discussed in the M-way tree. M is representing to any integer value. M is representing to a children value. How many child produces by a single node, that is called a order of M. So, a bee tree of order M can have at most M minus 1 keys. As I told you in the previous tutorial, in a M-way tree, M minus 1 representing the keys and M is representing the children's. Always children is 1 greater than the keys, and vice versa, key is 1 less than the as compared to children. So, at most M minus 1 keys and M children. This is standard formula. Either you working in a M-way tree, either you working in a bee tree. Here we having children M. So, definitely key values are M minus 1. Now, one of the main reason of using bee tree is its capability to store large number of keys. when we store corpus amount of data, when we're working out the big amount of data, we have to fit that data, that is called large number of data in a form of keys in a single node, and a large key values by keeping the height of the tree relatively small. In a MV tree, you doing same thing, you're feeding your data, you're inserting your data, but in that key, the height of that tree is not restricted. You can generalize any kind of height of the tree, you can create any kind of a level to level, height to height in any direction. There is no any restriction in MV tree, but here when we working, when we feeding, when we inserting a data in a MV tree by keeping the height of the tree relatively small as compared to the MV tree. We can see in the example why I am discussing this line, this topic, and how it will be beneficial for us when we feeding our data in a hard disk. Another point, a B tree of order M contains all the properties of MV tree. In addition, it contains the following properties. Now I am talking about the technical definition of B tree and how it will be more beneficial as compared to a MV tree. So the properties are, first point, every node. I am talking about each and every level. I am talking about the every node in every level. Each node in a B tree contains at most m children. If any node generating more than m children, which is given in the question, so it is not a B tree. So maximum producing children is a m. So no, you can't insert or feed children in a single node more than m. Now second point, every node in a B tree except the root node. Again I tell you, please mark this word, every node in a B tree except the root node and the leaf node contains at most m by 2 children. This is a restriction. This restriction is not covered in the MV tree, but this restriction covered in the B tree. It means you're talking about the internal nodes. You have to accept, it means you have freed at the root position or at the leaf position. Leave these positions, a part of this position, all the internal nodes. As we know that internal node is which type of node? It's a children of a root node as well as there's a parent of the another leaf nodes also. There's all kind of nodes are called the internal nodes. So internal nodes, the maximum internal nodes should be m by 2 children. It means when you putting the, suppose I draw a tree is a m equal to 5 by 2, it means 2.5, it means 2. Maximum 2 children, each and every node producing a 2 children, not less than the 2 children. So at least m by 2 children is mandatory each and every position of the node. At most it is completely depend on the order of m, but at least is a m by 2 children. And here m is an integer value, whatever the given in the question, you put this value and divide by 2, it will you find out the child, how many child will be produced at the internal node. Now third point, the root node must have at least 2 child nodes. It means when you fix any item as a root node, definitely it would produce both children. If it don't produce both children, it is not a form of a B tree. So it is a mandatory, any key which is available at the root position, it should be generated both children, left successor also and the right successor. If any key at the root node producing only a one successor, that is not a property of a B tree. It means it's a mandatory of every item of every node at a root node producing a 2 children. Next point, all the leaf nodes. I'm talking about all the leaf nodes. We already know what is the leaf nodes, which is not produce any children. So all the leaf nodes must be at the same level. It means when we hierarchy of any tree, at either a left tree, either a right tree, all the leaf nodes at the leaf level either left or right, all the nodes are on the same level. It means we can't say left one is the height is 2 and the right subtree height is 3. As when we comparing to the root node, height of left tree, height of right tree, both are the same. It means if a left tree height is 3, so definitely it is mandatory the height of right tree is also a 3. It means all the leaf nodes are on the same level. If any tree follow all the properties, this technical properties, it means should follow the principle of a B tree. If any one of the point is not following by the tree, it is not a B tree. So when any case will be arises, by the operation we have to shift by the logical operation to convert this kind of a tree into a B tree. So it is not unnecessary that all the nodes contain the same number of children, but each node must have m by 2 number of nodes. Not talking about the at most or at least, but we have to know the number of counts of at least node is m by 2. This is a mandatory. If any node not containing m by 2, at least m by 2 number of nodes, it is not a property of a B tree. So by this point, you have to understand the technical concept, what is the logic and what is the property of a B tree. One by one you can understand by the diagram what the points will be saying and how it will convert, how do we saying that is a B tree or not. So by B tree, by this example, this is order of 4 of a B tree. We have to understand this is a B tree of order number 4 or not. Here you see you having a root items and you are having also a left subtree and the right subtree. If you are talking about you having only single item is available, that is a root item. So as I told you, as per the properties of the B tree, except the root node and the leaf node, every internal nodes are m by 2. So here the order is 4, here m equal to 4. So the number of internal nodes are m by 2 means 4 divided by 2, it means 2. So all the internal node should be a minimum 2 keys, otherwise it will not represent the B trees. So here either I am talking about the as compared to left internal node, either a right internal node, both are the containing a 2 items, and the root items containing both children, and a left tree is also a non-empty and right tree also a non-empty, both having a children's, and the children's also internal nodes are the m by 2 by the factor of m by 2, it's a 2 at the left hand also, also we having a right hand side also a 2. When you are talking about another internal nodes like the first one also containing a 2 items, 29, talking about the internal nodes also contain left subtree and the right subtree, and each and every internal nodes, I am talking about the level number 1, all the items of level number 1 by we have to cross check all the items in the internal nodes containing both keys, containing both children's, either AI children, either AJ children, either left successor children, either a right successor children, each and every internal node containing both children in the should be connected by the key. None of the key or any hand is empty except the leaf node. All the internal nodes hands are completely packed by the some items. Clear? Now the last one, the last level, you have see all the children of the internal nodes are on the same level. So the height of the left subtree, or we can say the height of the right subtree, all should be the same. Left subtree and right subtree, both the structure of the height of the same. So this is a concept of a B tree. All the property, one by one we have to cross check all the property, it does definitely follow and obey the property of B tree. Again talking about this is a 4-way tree, it means a 4 order of m is order of B tree is m is 4. So firstly talking about the internal nodes, so we have to cross check internal node minimum item is 2, yeah, both are showing. Leaf nodes are on the same level, yes, also a same level. All the items or the root node item containing both children, yes, both children. It means, or also the leaf nodes are on the same level. It means all the properties of the, and one more point, not more than m children. You have cross check in every places, in anywhere, either root node, internal node or the leaf node, none of the producing more than the m children. So it means m is a 4, none of the stage will producing more than the 4. M is mandatory, M is compulsory. It means children maximum 4 will be produced by any node, that is okay. If any one node produce more than 4 children, it is not a follow the property of B tree. So by this example, you understand the concept of all the points. All the points are obeying in this structure. That's why we can say this tree is a B tree. Now, while performing some operations on B trees, as we know that all operation in a data structure are insertion, deletion, searching. This kind of operation we perform in each and every kind of a data structure. Same operation we can perform in this B tree also. So any property of the B tree may violate such as number of minimum children a mode can have. To maintain the property of B tree, the tree may split or join. So if you facing any difficulty when you inserting any item, either you inserting, either you deleting, when you performing any kind of operation, and the tree will be not balanced. So at that time you perform a such type of operation like either you split that nodes or either you join some nodes. That is again completely depend on these situations. What kind of situation will be arises, we will to take to help either a parent node, either a sibling node, either a grandparent node. If anyone can help you, then tree may be a split, then tree may be a join. Again depend on the situation of the tree structure when we performing a data structure operation. As you know, data structure operation are searching, insertion and deletion. So first we go for the first operation, that is called a searching. By this tree structure you can understand the concept of how we performing a searching operation. Searching is nothing else, not updating something, you just go and search that particular item is available or not available. If item is available inside that particular tree, by the structure of that tree, you obey the principle of tree. If any item when you finding something, it is available, it means the operation is successful, otherwise your operation is unsuccessful. So item is available, it means successful operation, either is not available, it is an unsuccessful operation. So how we perform a searching operation in a B tree is similar that in a binary search tree. As we know that how we create a binary search tree, all the smallest item are connected at the left subtree and the right item connected at the right subtree. So same kind of a phenomena will also property of follow by the in a B tree by the principle of binary search tree. By this example we can understand, if we search for an item 49 in the following B tree, the process will something like following. First, you fix your pointer at the root node and compare your new item, your searching item with that the root node. Here we are having a root node item is 78. Now compare the item, searching item, that is a 49 with a root data, and root data is a 78. So 49 is less than for 78, hence item should be available, may be available at the left hand subtree. So we shift our pointer and move to its left subtree. Okay. Now go for the second one. Now second internal nodes. Here we are having internal nodes are 40 and 56. So again we starting the comparing operation. First we compare with the first item, that is called a 40. So 49 is greater than 40. So our pointer will be jumped to the next item, that is called a 56. Now 49 is less than the 56. So it should be, we have to understand 49 should be lie in between the 40 and 56. So we have to cross check the children in between the 40 and 56. So 49 definitely may be available in between the 40 and 56. It will follow the child of 40 and between the 40 and 56 child. So traverse the right subtree of 40, or we can say left subtree of 56. So again we compare with the first item, that is called a 45. Now 49 is greater than 45. So definitely our pointer will be shifted to the next item, to the neighbor of that particular 45. So move to the right side and compare with the 49. Here 49 is present over there, and the searching item 49 comparing with that item, and 49 will be matched. It means item your searching operation is successful, match found, and return back to your first step. You can write the statement your operation is successful. 49 is available in such a position in a B tree. So searching in a B tree depends upon the height of the tree. The search algorithm takes O of log n time to search any element in a B tree. It will directly proportional to the time complexity as well as the space complexity. By this operation, you can search your item in a very smoothly and a smartly way. By this, you can search any item in this tree, either a left tree, either a right tree. Suppose you are finding the last one, the 110, by this fix your pointer at the root node and compare with that item, then pointer will be shifted to the right hand side, again comparing with that item, the item is again the bigger than all the item, again the pointer will be shifted at the leaf node, again we comparing with all the item and you find out the when the item is available, it means the searching is successful. If item is not available, the operation is unsuccessful. So this is a way how to perform a searching operation. You can't update anything. You just searching either the item is available or not available. If item is available, to which position? You have to display the position of the in which area item is available in that particular tree. I hope understand the concept of searching operation in a B tree. Now we go for the second operation, that is called a insertion. So insertion are done at the leaf node level. The following algorithm needs to be followed in order to insert an item into a B tree. I am talking about point by point how we going to perform an insertion operation and which kind of operation, traversing operation also required for when we perform an insertion. Traversing and searching both are required to inserting the position, find the position and inserting a new data into a B tree. The first point is that traverse the B tree in order to find the appropriate leaf node at which the node can be inserted. First should be inserted at the leaf node. If the leaf node contains less than m-1 keys, again understand, if the leaf node contains less than m-1 keys, then insert element in the increasing order. As I told you, as the M-way tree, all the item when you feeding, when you inserting in a B tree should be following the ascending order, or we can say the increasing order. The data should not be placed anywhere, any position randomly. It should be placed as per the ascending orders. So you have to cross check m-1 keys is available or not. If m-1 keys is available, then you go for the insertion operations. Else, if the leaf node contains m-1 key, then follow the following step. Sub steps are: first you done, insert the new element in the increasing order of the elements. Then split the node into the two nodes at the median. Suppose when you inserting some data and that data particularly enhance the length of the node. Suppose the order is 4 and you after you inserting that element, so it should be a children is a more than 4, that is a 5, and keys are the 4. It should not follow the property of B tree. At that time you split that nodes and you find out the middle items and push the medium element up to its parent node. As I told you, when you facing any difficulty, you always help with the parent. If parent can fulfill your demand, that is okay. If parent is again not give you facility, you will take care and help from the either a sibling, either a grandparent also. That is completely depend on this situation. We can see this such kind of a situation later in the next slide when we are performing any operation in a B tree. By that operation, we can understand the concept of this one. So when you are facing any difficulty like that, so split the nodes into the two nodes at the median, push the median element up to its parent node. If the parent node also contain m-1 number of keys, that is again worst situation. Parents, you taking a help, but parent are not having a facility to fulfill your demand. Maybe parent also facing. So at that time you will take again help to its grandparent, like that. Again you performing the same operation in a parent node. You split it 2 by following same step. and again find out the median value. When you find out the median value, you can separate the left successor and there is a right neighbor in the different end, and pick that median value and push to its parent value. It means we can say that particular item will be shifted to the grandparent, and by this approach your tree will be a balanced tree. It means after you inserting, after you pushing the tree, the main concept is that the tree follow all the 4 points which is talking in the earlier slide, all the 4 points, technical point, which is follow the property of a B tree. If you after you pushing an item, the tree is not following B tree concept of properties of B tree, it's not a B tree. So this is a theory concept. We can understand by the diagram how when we performing any operation. I'm talking about how we identifying the median item, how we pushing that item, how we take an help from the parent, how we take from the grandparent, how we take from the sibling also. That will be understood by the upcoming diagrams. So we can for this point we can understand the one example, understand how we performing any kind of a operation. So first we go for the insertion and insert the node 8. It means we already take a item in a new node from the free space memory, and we have to insert this item 8 into a B tree where the B tree of order is 5. So as showing in the figure, this is a B tree diagram of order 5. So this is order 5 tree, and we have to insert a new item that is called a 8. So one by one we have to cross check. First we perform a traversing as well as the searching operation. By the searching operation we have to find out the location where we have to insert a new item 8 into this tree. So again we start for the searching the location. We fix our pointer at the root node and then start with the comparing. Now our new item is 8. Now again you comparing from the root item, the new item should be lie at the left subtree of the root item and the left subtree are the 29. So again 8 is less than the 29, then again you should be in lie and maybe inserted at the left subtree of 29, and the items are available are 3, 5, 10 and 23. So 8 is when you comparing with the first element, that is a 3, 8 is greater than 3, that's why pointer will be shift to the neighbor of 3, that is a 5, and again we cross check 8 is greater than 5, again pointer will be shifted to the next neighbor of that node, that is a 10, and 8 is less than 10, it should be at space is located, you find out the location, 8 should be inserted in between 5 and 10. Before you inserting, you have to cross check, can we insert a new item, new data inside the node or not. Here we having a node of order is 5. So already the minimum keys are available as per the principle of B tree, that is a m-1. So m-1 the order is 5, that's why maximum keys is available in any node, that is a maximum is 4, at most 4, at least it is m/2. So at least m-1, that is already a 4, already 4 items is available before we inserting a new item in this node. So this is a little bit complex situation. So what we do? First we insert a 8 at the same position. It means where it will be located, should be inserted in between a 5 and 10. After inserting 8 in that particular node, 3, 5, 8, 10 and 23, which is not follow the property of a B tree, not obeying the principle of a B tree. So what we do? We, as per the principle, when after inserting a new element in any node, the tree is not satisfying the principle of a B tree, it exceed the size of a key. Here the node size is exceeding the size of 4, it means our now item is the 5, which is not satisfying or for this particular tree where the tree order is m equal to 5. So in same situation, when children facing some difficulty, it should to take a help from the parent. Now what we do? We, as per the principle, as per the theory, we find out the median element. So after inserting a 8 in that particular node, we find out the median item. What is the median item? Here we having a 5 elements, 3, 5, 8, 10 and 23. If we are talking about the median item, the median item is 8. Now again check. So when you fixing your item 8 as a median item, so pick that item, because after inserting a 8, that tree is unbalanced, which is not following the property of B tree. So pick that value 8. 8 is a median value of that particular nodes in between 3, 5, 8, 10 and 23. So we pick that value median item as a 8, and after picking that item 8, we push that item to its parent node. So parent node already 29 and 32 is there. So we insert that median item as a left neighbor of a 29, or we easily insert that 8, because as per the property, as per the principle, we can insert maximum item, maximum keys are 4, and after inserting a 8, the quantity of item is only a 3. So we can easily insert that item, median item, into a left neighbor of a 29. So after inserting a 8 at that position, again the left neighbors of 8, that is a 3 and 5, are connected as a left subtree of a 8, and right neighbors of a median item, that is a 10 and 23, are connected as a right successor of 8. So after splitting the nodes, and we pick that median item or pushing that item, and also connected the left successor item also and right successor item also. As we know that at the principle of the B tree, we can't insert an empty of any hand. We have to fill all the hands of any internal nodes. So again, after pushing this operation, picking and pushing that operation, again you cross check is this tree is remain a B tree or not. So one by one you can check. After inserting a 8, is this tree are following the property one by one? All the leaf node are the same level or not? Yes, all the leaf node are the same level. All the internal node, at least m by 2 children and at most m children. Yes, it should be following the property. Heights of all the tree are the same. Yes, height all are the same. Root node carrying both child. Yes, root node carrying both child. All the internals carrying both child. Yes, all children are both child. It means all the property which we are already talking about, this is all properties, all the points are following in this B tree after inserting a new item 8. So we can say after inserting a 8, this is called a B tree. So I hope you understand the concept of a B tree, how it will be useful for us, how it is an extended version of an MV tree, how we performing any operation like searching or insertion. Today we discuss two operation, insertion and searching. Searching as it is like a binary search tree. Insertion is a little bit complex, not we directly insert and as like a MV tree. Here we have to insert at the appropriate position, but we have to cross check the at least or at most way of the children. If the size is exceed of any node more than m children, you should be find out and take that median data and push into a appropriate position of any structure of a parents. You can take a help of parents also and anywhere also. So by this operation you can understand the concept of this particular B tree. So we can understand future next operations like deletion, or also we understand the concept of when we can do the lots of operations of data structure operation inside the B tree. This is very useful for you. This is definitely in a university question papers, in everywhere lots of question are arises from the B tree. A part of the university's paper, most of the question are in a MCQ's paper, also questions arises from the B tree concepts also. So by this topic you can understand the concept of trees, and right now the scenario, the world market, all the structure we can working on the based on the concept of a B tree or a B plus tree, we feed our data. So in the future class we understand the concept of the future operation like a deletion and the operations part, that we cover in the next class. For today's tutorial introduction, For this, thank you.